All right, you are welcome again. Today, let's consider limit. Okay, let's take a look at this question. Show that the limit as x approaches infinity, a raised to the power of 1 all over x plus b raised to the power of 1 all over x all over 2, close the bracket, raised to power x is equal to the root of ab. Okay, the root of AB. So this is what we are asked to show. That is, you are asked to simplify or evaluate this limit. Okay, now let's take a look at this very carefully. We are going to solve it. Actually, it's very long. The solution is very long, but I will solve it step by step and bit by bit. I want you to pay attention as we do this together. Please, if you are new to our YouTube channel, please do well to subscribe, like the video, and then also share to your loved ones. Okay, now let's go. Solution. Here we want to evaluate this limit. Look at what we do. First of all, we say let y equal to the function we have, which is a raised to the power of 1 all over x plus b raised to the power of 1 all over x all over 2. Okay, all a bracket raised to the power of x. This is the function we have, and then we say let y be this function. So the next thing we do is we take the natural log on both sides. So taking the natural log on both sides, that means we are going to have ln y is equal to ln the right hand side, which is a raised to the power of 1 all over x plus b raised to the power of 1 all over x all over 2 in bracket raised to the power of x. Okay, now if this is true, look at it. Under logarithm, you see the power raised to the power of x. We bring it behind the ln. Okay, so coming, that means we have x ln a raised to the power of 1 all over x plus b raised to the power of 1 all over x all over 2. You get right? Good. Now let's go. From here, we can take the limit of both sides. Taking the limit on both sides, we are going to have limit as x approaches infinity, ln y is equal to limit as x approaches infinity, x ln a raised to the power of 1 all over x plus b raised to the power of 1 all over x all over 2. Okay, good. Now look at it. Let's consider the right hand side. So the right hand side we are going to have is the same thing as saying all over 1 all over x. You see how we do this? It's the same. Now look at the left hand side. We will pass the limit inside the function. Okay, so that means we are going to have ln open bracket limit as x approaches 0 y, all right, equal to, this is what we have. This ln open bracket a raised to the power of 1 all over x plus b raised to the power of 1 all over x all over 2 all over 1 all over x is the same as what we have above, because this all over is talking about divided by 1 all over x. So when you change the division to multiplication, you perform inversion. That means 1 will come down and then x will go up. Okay, so you see that it is the same. All right, good. Now let's go. Now, using L'Hospital's rule to evaluate this limit in a right hand side. Now, L'Hospital's rule states that we are to evaluate our numerator by differentiating it separately, and then also differentiate our denominator separately. Okay, so when we do it the first time, we plug in our limit and see what it gives us. If it still gives us 0 all over 0 or infinity all over infinity, we do it the second time, repeat it the third time. Okay, now let's do this for the first time. Let's see what we are going to have. Now, working with the numerator, let's pick the numerator and evaluate. That is, pick the numerator and differentiate it. So picking the numerator, we are going to say let z be our numerator. So that means this z that is our numerator now, we are asked to find the z dx. Now looking at this function, we are having the variable x in it, right? And then we say let's call it z. So for us to find the derivative or for us to differentiate it, that means we are actually looking for the z dx. Is that true? What we want to find here is the z dx, the derivative of z with respect to x. Now let's go. For us to do so, it looks a bit complex, right? Good. For us to evaluate this, we are going to apply chain rule. Chain rule. Everything inside this bracket, we call it a letter. Let's say u. That means we are going to have let u equal to, we have a raised to the power of 1 over x plus b raised to the power of 1 over x all over 2. Okay, good. Now, in this place we have u. That means we are going to differentiate this u with respect to x. All right. Now, coming back again in this z, we see that we have z is equal to ln u. All right. So here we are going to differentiate z with respect to u, and then we differentiate our u with respect to x. Multiply two of them, it will give us the z dx. Hello. Look at it. We say z is equal to ln u now because we replace a all over 1 over x plus b raised to the power of 1 over x all over 2 with the letter u. So here we have ln u. We are going to differentiate this z with respect to u and then go to the function u, differentiate the u with respect to x. Now multiply these two derivatives. It's going to give us the z dx. Is that clear? Now let's go. Let's take them one after the other and do so. Let's go to our u. For us to differentiate u with respect to x, look at it. First of all, let's factor out 1 over 2. So when we factor out 1 over 2, it's the same thing as saying u is equal to 1 over 2, open bracket, a raised to the power of 1 over x plus b raised to the power of 1 over x. Okay, good. Looking at this, you see that 1 over 2 is a constant. Okay, let's put it by the side. So here we are going to differentiate a raised to the power of 1 over x. Then say plus differentiate b raised to the power of 1 over x. Is that clear? Then multiply by the constant 1 over 2 that is outside. Let's pick it one after the other and differentiate. Let's differentiate a raised to the power of 1 over x first. Going, we are going to say let p be this a raised to the power of 1 over x. We want to differentiate it now. All right, we want to differentiate a raised to the power of 1 over x. Now we say let's call it p. So that means we are going to find the p dx, the derivative of p with respect to x. That is the derivative we are looking for. Now, carefully looking at this, we see that a raised to the power of 1 over x, we cannot simplify it directly. So we have to, or we cannot differentiate it directly. We have to employ chain rule again. Good. So for us to employ chain rule, we are going to say let t equal to 1 over x. This 1 over x that makes this a raised to the power of 1 over x to be a bit complex, let's call it a letter t. So as we call it a letter t, that means we have p is equal to a raised to the power of t. I think it's very simple now, right? Good. So here, now let's go back to this our t. In this place we say let t equal to 1 over x, right? We differentiate t with respect to x. Okay, good. As we differentiate t with respect to x, it's going to give us minus 1 over x squared. Is that true? Yes. Please pay attention. This is elementary derivatives or elementary differentiations. Now look at it. We say t is equal to 1 over x. We find the t dx. So to express or to find the t dx, we say that it is minus 1 over x squared. Okay. Now let's go back to p. In this place we say p is equal to a raised to the power of t. We differentiate p with respect to t. So when we do so, we are going to have dp dt is equal to at ln a. Hello. We say that dp all over dt, that is the derivative of p with respect to t, is giving us a raised to the power of t ln a. Do you get? Good. Now look at it. We want to evaluate du dx. Okay? We want to evaluate du dx. And then we started by evaluating the variables, the values one after the other. So the first one is a raised to the power of 1 all over x. So we say let this a raised to the power of all over x be called the letter p, right? Good. So for us to evaluate this p, we said we are going to find the p dx. So we apply chain rule. Chain rule, we first say let t equal to 1 all over x. We differentiate it, we have minus 1 all over x, right? Good. Again, this p now, as we replace 1 all over x with a letter t, that means we have p is equal to at. We also differentiate this p with respect to t. So we have dp dt is equal to a raised to the power of t ln a. So bringing these two derivatives together, bringing the p dt times the t dx together, it gives us the p dx. Hello, look at it. Look at it. But you see that t is equal to 1 all over x, right? Good. And then we see that when you replace it, that means we say that dp all over dt is equal to a raised to the power of 1 all over x ln a. You get this, right? Good. Now let's go. We see that the p dx that we are looking for, which is the derivative of a raised to the power of 1 all over x that we are looking for, is actually the multiplication of these two derivatives that we have by employing the chain rule. What are these two derivatives? We say dp dt multiplied by dp dt. What do we say that dp dt is? Dp dt is what? Is a raised to the power of 1 all over x ln a. All right? Good. Multiply by, what is the t dx? The t dx is minus 1 all over x squared. Okay? So when we multiply this together, this is what we have, right? Good. Now look at this. We see that this dp dx is actually the derivative of a raised to the power of 1 all over x. All right? Good. So here we say we are looking for du dx. We are looking for what? Du dx, which is going to give us 1 all over 2 open bracket. When we differentiate a raised to the power of 1 all over x, it gives us a raised to the power of 1 all over x ln a multiplied by minus 1 all over x squared, plus when we differentiate b raised to the power of 1 all over x, it's still going to give us the same value as of what we have here. Okay, it's going to give us the same value like what we have here, but the difference is a and b. So here we're going to have b raised to the power of 1 all over x ln b multiplied by minus 1 all over x squared. Is that clear? Yes. So here we see that du dx, the derivative of u with respect to x, is 1 all over 2 open bracket. We have a raised to the power of 1 all over x ln a times minus 1 all over x squared plus b raised to the power of 1 all over x ln b times minus 1 all over x squared. All right, good. So here now we have minus 1 all over x squared in both a and b. We factor out this minus 1 all over x squared. All right, let's factor it out. As we factor it out, this is what we have. We have the u dx is equal to 1 all over 2 open bracket. When we factor it out now, we have minus 1 all over x squared open bracket. We have a raised to the power of 1 all over x ln a remaining. All right, plus b raised to the power of 1 all over x, ln b remaining in the part of b. Is that true? Yes. Now let's go. You see that what we just did now is actually the derivative of the first part of z. All right? The first part of z. We wanted to differentiate z, right? And then we say that z is equal to ln a raised to the power of 1 all over x plus b raised to the power of 1 all over x all over 2. All right? And then we apply chain rule, right? And then we say let the content in this bracket be called the letter u, and then we differentiate this u with respect to x, and this is what we have now, right? Good. Now the second part of this z now, where we have z is equal to ln u. So let's differentiate this z with respect to u. So when we differentiate this z with respect to u, it's going to give us dz du is equal to 1 all over u. When we differentiate ln u, it's going to give us 1 all over u. All right, good. Now look at it. The derivative of z, which is our numerator, we want to find, is going to give us these two derivatives that we just obtained. The derivative of z with respect to u multiplied by the derivative of u with respect to x. You get? Look at it. We say that the z dx is equal to the z du multiplied by du dx. All right, good. Now let's bring these two together. Where we have multiplied them, we bring them together. Okay, so bringing them together, we see that the z dx is equal to the first part, or this one we just differentiated now, which is the z du. What we have, we say it is 1 all over u, then multiply by the u dx that we just differentiated. So it's going to giving us 1 all over 2 open bracket minus 1 all over x squared open bracket a raised to the power of 1 all over x ln a plus b raised to the power of 1 all over x ln b. All right, good. Now let's go. Now in this case, we see that the z all over the x is actually the derivative of our numerator. This is just the numerator. Okay, now let's go. What about our denominator? Our denominator, we are having 1 all over x. So when you differentiate 1 all over x, it's going to give you what? Minus 1 all over x squared. Okay, now look at it. This is actually what we are doing. We have ln open bracket limit as x approaches infinity y is equal to limit as x approaches infinity ln a raised to the power of 1 all over x plus b raised to the power of 1 all over x all over 2 all over 1 all over x. And what we just did now is that we differentiated our numerator, and then we say if we differentiate our denominator, that is going to give us minus 1 all over x squared. Is that true? So now bringing the derivative of the numerator and the derivative of the denominator together, now what are we going to have? We are going to say that we have limit as x approaches infinity. We have 1 all over u multiplied by open bracket 1 all over 2 times minus 1 all over x squared open bracket a raised to the power of 1 all over x ln a plus b raised to the power of 1 all over x ln b all over minus 1 all over x squared. Hello. All right, good. Now watch this carefully. You see that in our numerator we have minus 1 all over x squared that we factored out, right? Good. And then also in our denominator we have also 1 all over x squared in negative form, right? Good. So you see that this minus 1 all over x squared will cancel both in numerator and the denominator. All right, so when they cancel, that means there is only one in our denominator, right? Good. So it's the same as linear. All right, good. Now look at what we have here. Now we have limit as x approaches infinity open bracket 1 all over 2 times 1 all over u open bracket a raised to the power of 1 all over x ln a plus b raised to the power of 1 all over x ln b. All right, good. Now look at it again. Let me show you something. You see this place we have 1 all over u. You know, it's still the same thing as a 1 divided by u. Is it true? Yes. Now, but you remember there was a place we say u is something. Okay, you remember? Yes. Look at it. We say that u is equal to a raised to the power of 1 all over x plus b raised to the power of 1 all over x all over 2. We bring it back. Okay, so that means we are going to have limit as x approaches infinity 1 all over 2 multiplied by 1 divided by, in place of u now, we have a raised to the power of 1 all over x plus b raised to the power of 1 all over x all over 2. All right, good. Multiply by, you see what we have again, a raised to the power of 1 over x ln a plus b raised to the power of 1 all over x ln b. All right, good. Now look at this. This division we have here, this 1 divided by, we can turn this divided to multiplication. So as we turn it to multiplication, we perform inversion. All right, so in this small bracket where we have a raised to the power of 1 all over x plus b raised to the power of 1 all over x all over 2. So the denominator will come up and then the numerator will come down. Okay, so doing so, this is what we have. So here we have limit as x approaches infinity 1 all over 2 times 1 times 2 all over a raised to the power of 1 all over x plus b raised to the power of 1 all over x, all right, in bracket, times a raised to the power of 1 all over x ln a plus b raised to the power of 1 all over x ln b. All right, good. Now let's go. In this case now, carefully looking at this, we have 2 in a numerator and 2 in a denominator. All right, they will cancel out. So when they cancel out, this is what we have. We have limit as x approaches infinity 1 all over a raised to the power of 1 all over x plus b raised to the power of 1 all over x in bracket multiply by a raised to the power of 1 all over x ln a plus b raised to the power of 1 all over x ln b. All right, good. When we multiply these two together, it's going to give us a fraction that looks like this. We have limit as x approaches infinity a raised to the power of 1 all over x ln a plus b raised to the power of 1 all over x ln b all over a raised to the power of 1 all over x plus b raised to the power of 1 all over x. All right, good. Now let's go. From this place now, we can confidently plug in our limit, okay, our value for the limit. So we say as x approaches infinity. So anywhere we see x now, we can plug in our value for x, right, which is infinity. Let's go. Here we have a raised to the power of 1 all over x. In place of x, we write infinity. Then we have ln a plus b raised to the power of 1 all over x. We have 1 all over infinity ln b all over a raised to the power of 1 all over, in place of x, we say infinity, plus b raised to the power of 1 all over x. In place of x, we say infinity. All right, good. Now look at it. Anywhere you see 1 all over infinity is 0. All right, so here where we have 1 all over infinity, 1 all over infinity, the value is going to give us 0, 0. All right, so in the first place, we have a raised to the power of 1 all over infinity, which is where 1 all over infinity is 0. That means we have a raised to the power of 0 is going to give us 1, because any number raised to the power of 0 is what? 1. So here we have a raised to the power of 0 is equal to 1. Okay, good. And then in the side of b, it's also going to give us 1. In the denominator, we are going to have 1 plus 1. Is that clear? Good. Now let's go. In the numerator, we have 1 times ln a plus 1 times ln b. It's going to give us ln a plus ln b all over 2. Okay, is equal to. Now look at this. You know, in logarithm, when you have log xy, you know it's the same thing as saying log x plus log y. Hello, is that true? Yes. Now if this is true, now look at what we have here. We have ln a plus ln b all over 2. we are permitted to write it this way, to say that it is the same as ln AB all over 2. This is logarithm. Okay, good. Now, if this is true, we can factor out 1 all over 2. That means we have 1 all over 2 ln AB. Is that true? Yeah, you remember in the law of logarithm again, we can take this 1 all over 2 that is behind the log, which is ln, to the exponent. Okay, so when we take it to the exponent, we have ln AB raised to the power of 1 all over 2. Is that true? Yes. Now let's go. You know, all these things we have been evaluating is actually ln, open bracket, limit as x approaches infinity y equal to limit as x approaches infinity ln, open bracket, a raised to the power of 1 over x plus b raised to the power of 1 over x all over 2 all over 1 over x. And then we see that this right hand side is what we have been evaluating. And then at this point, we have obtained that this right hand side is equal to ln AB raised to the power of 1 over 2. Is equal to ln AB raised to the power of 1 all over 2. Okay, good. You know, from the beginning, we take the natural log, right? From here now, we are going to remove the log by taking the anti-log. By taking the what? The anti-log. How do we take the anti-log on both sides? We are going to simply say it is the same as e raised to the power of what we have. Okay? E raised to the power of, in our left hand side, we have ln, open bracket, limit as x approaches infinity y is equal to, in our right hand side, we say e raised to the power of ln AB raised to the power of 1 over 2. So this e and the ln, or e raised to the power of ln, is going to give us 1. Okay? It's going to cancel. All right? Good. So when it cancels, look at what we have. We are going to have limit as x approaches infinity in the left hand side, y is equal to, in the right hand side, we have AB raised to the power of 1 over 2. And then you see that this raised to the power of 1 over 2 is the same as, say, root AB. Is that true? Yes. But remember, when we started, immediately we say solution, we say let y equal to something. We say let y equal to a raised to the power of 1 over x plus b raised to the power of 1 over x all over 2 all in bracket raised to the power of x. And here we're having lim as x approaches infinity y. So that value, we place it back now. Okay? The value for y, will bring it back. So that means we have limit as x approaches infinity. In place of y, we have a raised to the power of 1 over x plus b raised to the power of 1 over x all over 2 all in bracket raised to the power of x is equal to root AB. Yes, we have proved. Hence the proved. So this is very simple. Take this step by step gradually, and then you master it. All right. Thank you very much for watching. Let's take more videos. Let's take more lessons on different topics. All right. Please, if you are new to our YouTube channel, like, subscribe, and share our videos. Stay blessed. See you some other time.